covered that how to use the discrete wavelet transform in images, and then we had also planned to cover that how the DWT coefficients are actually encoded in order to generate the bit stream. Now, we could not exactly cover to the extent we had desired in the last class because of some shortage of time. So, we are going to continue with that in this lecture, and the title that we have for this lecture is Embedded Zero Tree Wavelet Encoding. Now, towards the end of the last lecture, I had actually introduced to you the concept of the parent-child relationship that exists between the coefficients in the different subbands, all right. And especially we had seen that whenever we are changing from one resolution to the next, okay, to the more finer resolutions whenever we are going, there we are finding that one pixel or one coefficient in the coarser resolution or coarser scale that corresponds to 4 coefficients in the next final level of scale. Okay. And this is what will form a kind of a tree, okay, where the root node would be the coefficient that belongs to the topmost level of the LL subband. Okay. So, we are essentially assuming a dyadic partitioning where the LL subbands are successively split into 4 more subbands, and each LL is iteratively subdivided further. And then we had seen that how to obtain that kind of a data structure, and essentially that data structure exploits the coefficient, the relationship that exists between the coefficients in the different subbands, and this is what we are going to exploit in the encoding of the DWT coefficients. Now, to encode the DWT coefficients, actually we are first going to discuss about a very popular technique which was proposed by Shapiro, okay. And there is a very classic paper written by Shapiro. So, let me give you first the reference of the paper, so that you can yourself go through and find out details which are more than what we will be able to cover in the class actually, because in the class I will be giving you the essence of the algorithm in a nutshell way, but more details of it you will find in this paper. The paper is written by Jerome M. Shapiro. He is the author of the paper, and the title is Embedded Image Coding using zero trees of wavelet coefficients. Now, the term zero tree is not yet known to us. Tree is known because we have just described that what a tree structure is going to be in terms of the wavelet coefficient. In terms of the zero trees of the wavelet coefficients, and as I was telling you, this is a classical paper and it appeared in IEEE Transactions on Signal Processing. You can find it in volume 41, number 12, December 1993, and the page numbers are 3445 up to, let me tell you the last page of the paper, it is 3462. So, the paper is actually 17 or 18 page paper, fairly long one, but I mean after you listen to this lecture, okay, it will be quite instructive to go through this paper and have a more detailed feeling. Now, first essential philosophy behind this embedded zero tree coding is that you see that what is our objective? We want to achieve compression, and to achieve the compression, as you know that we have to exploit the redundancy, and in this case the redundancies are exploited between the coefficients which are there in the same pixel location, but in the successive subbands. What I mean to say is that in the last class you had seen that if we have a dyadic partitioning like this. So, if this is the first level of decomposition, and then we go through the second level of decomposition and third level of decomposition and so on. So, what we do is that we pick up the coefficients from the topmost LL subband, which is this one, okay, and then we form a tree where the descendants would be first the HL, LH and HH coefficients in the same resolution, and we will be picking up those coefficients in this order. That means to say that first start with this as the root node, go over to this, explore this, pick up this the corresponding coefficient in this subband, pick up the corresponding coefficient in the next subband. Corresponding means corresponding spatial position, because this coefficient which you are picking up from the LL subband is having a coordinate in the LL subband. So, have the same reference coordinate in all the successive subbands in this order of coverage. So, the order is LL, HL, LH, HH. Then you go over to the next HL subband. Okay. Here you have to pick up the 4 coefficients, because each coefficient here would correspond to 4 coefficient here. Then pick up this 4 coefficient, pick up this 4 coefficient, pick up this 16 coefficient, this 16 coefficient and this 16 coefficient. Now, at the same spatial position, okay, we have picked up the coefficients at different resolutions, at different scales of wavelet filtering. Now, why are we doing that? As I was telling you that we will be finding that most of the coefficients are highly significant in the low frequency subbands. That means to say that in the LL we will be finding almost all the coefficients to be highly significant, okay. And as we go on to the finer and finer resolution, and that too in the high pass filtered subbands, okay, we will be finding lesser and lesser significant coefficients. So, there is a possibility that we will be picking up I mean considerable number of insignificant coefficients or zeros, okay, when we traverse down this tree. Now, there is a great trick, okay, which has been suggested by Shapiro, and that goes like this, that since you are traversing in a tree like this, okay, you form a tree first, and then whenever you are traversing a tree in this order, if you are finding that a particular coefficient at the higher level of subbands, that means to say that here if you find that any coefficient is insignificant, let us say 0, okay, and if you find that all its descendants in the tree are also 0, in that case there is no point in encoding each and every 0 coefficient. You can say that okay, beyond this everything is going to be 0, everything in this tree is going to be 0. So, that is what forms a 0 tree. 0 tree means, okay, where I mean 0 tree is a part of a tree structure where all the elements, okay, starting with some intermediate level of parent, some intermediate parent node, okay, will have its own value as 0 and all the subsequent descendants to it as zeros. If you find some kind of a node like that, then that node is defined as a 0 tree node. Okay. And the embedded 0 tree wavelet coding essentially makes use of that philosophy. So, that is the origin of the name 0 tree and why is it embedded. You see that whenever we are encoding the coefficients, okay, we have to cater for what? We have to cater for certain bit rate, that the channel in which we are transmitting the bits, okay, the encoded bits, that channel is having some limited bandwidth. Now, one may have some a priori idea about that channel bandwidth, okay. One may not have a priori idea of channel bandwidth, and even if one has a priori idea of channel bandwidth, it is so possible that I mean that changes dynamically. At some point of time you may get higher bandwidth, at some point of time you may get lower bandwidth. You must have experienced while accessing the internet, you must have experienced that sometimes you are really feeling very happy that you are getting excellent internet speed. So, you are telling your friends that today the net is really excellent, I am downloading everything in a flash, and then within 5 minutes time you may find that your computer is not giving any response, because by then the internet sites have become slow and you are having very less bandwidth. Maybe that at that point of time you will find that it is downloading at 1 kilobits per second rate, sometimes it may be downloading at 100 kilobits per second or even higher rates than that. Now, I mean all that I want to say is that even whenever you are making some image transmission over the net, encoded image transmission over the net, this thing can happen. So, in that case what one has to do is that one has to adjust the quality of the image accordingly. Well, if the bandwidth is higher, in that case give a good quality. If the bandwidth is poor, feel satisfied with a cruder quality of the image. Okay. So, in order to do that, what one does is to go in for an embedded coding. The philosophy is that you generate the bit stream in a prioritized order. By prioritized order, I mean to say that judiciously you select that which coefficients are very much significant. So, more significant coefficients you transmit first and then you transmit the lesser significant coefficients. The beauty of this scheme is that, well, if your bandwidth is good, you can go till the end. You can encode the priority coefficients and lesser priority coefficients, everything, get the best quality. If you have a very limited bandwidth, after transmitting the priority coefficients, if you find that your bit budget is exhausted, you do not have bandwidth beyond that, so you truncate the bit stream there. At any point of time, you should be able to abruptly truncate the bit stream, and that should be able to generate a reasonably good quality image. It would be best quality image, okay, because we are truncating something, we are chopping off some information, but it will be reasonably good. Okay. So, that kind of a truncation at any arbitrary point of encoding should be possible. That is the philosophy behind the embedded coding. Now, because we have already gone through the discrete cosine transforms, okay, think over, could we do that in the DCTs, in the normal DCTs? Okay. I mean, if we try to do the zigzag scanning and at some point of time, I mean, after some coefficient, after some coefficients in the macro block, if I find that my bid if my bid budget is exhausted, okay, then I have to abruptly truncate that. And furthermore, I mean the worst situation would be that whenever I have picked up the transform coefficients, okay, and then I am doing the quantization and then encoding it using some entropy coding scheme, okay, and there while the entropy coded bit stream is going on, I have to truncate the bit stream. I mean I may lose lot of information and my quality could be disgracefully bad. Okay. So, in order to avoid that, one can make use of an embedded coding scheme like this, and Wavelet very interestingly is amenable to such kind of embedded coding scheme, okay, as proposed by Shapiro. Now, what is the essential philosophy behind this? Now, as I was telling you that what is after all a zero tree root, although I have said that, but just a very small example. Okay. Supposing I find that this coefficient value is let us say minus 17 and say its descendants are 4, minus 1, 7, 6. Okay. Now, supposing its descendants one of its descendant is 0, then 6, minus 5, etc. Okay. Now, here I find that when I explore this, okay, I find that all its descendants are zeros. If I explore each of this, I find that all of these are zeros. Zeros means insignificant, okay, sort of an insignificance. Now, how that insignificance is decided, that part we will come very shortly, but in this kind of a situation, we would say that this particular node, this forms a zero tree root, okay, because beyond this, so there is a zero tree which is formed like this, okay, and this is a zero tree root. Now, zero tree root means that its value is 0 and all the descendant values are 0. Now, let us say that anywhere here, that supposing here I find that this value is minus 5 or this value is 6, let us say that here I have a value of 0 and then I have minus 2, I have got plus 7, I have got 16, and supposing here its children are minus 5 to 0, 8 like this. Now, this is not a zero tree root. Why? Because this is not forming a zero tree, because beyond this, I mean beyond its descendants, we are again having some significant coefficients. Now, how is the significance decided? The significance is essentially decided by comparing the magnitude of the coefficient. Now, the coefficient could be positive or negative, because you know that in the process of wavelet filtering, okay, we are using the scaling filter, we are using the wavelet filter, and the values could be positive or negative, okay, and in the process of doing that, we will be picking up, okay, I mean because the values could be both positive and negative, that is why it is a good practice to compare with the sign, with the magnitude. So, if I have a coefficient value, let us say capital X, okay, what we do is that we compare this value of x with a quantity t, where t is the threshold. Now, we define that if mod of x is less than t, in that case it is declared as insignificant, okay, and if mod of x is greater than t, then it will be called as significant, or just to take care of the equal to case, we can say that, okay, mod of x greater than or equal to t makes x as a significant coefficient. So, significance or insignificant could be a binary decision. In fact, I mean that is how I should have framed the example. Okay, I had shown numerical values, okay, but you can say that, okay, rather than considering this minus 6, 5 and all these things, 6 minus 5 and all these things, you could I mean take it to be all of the others to be significant and insignificant. So, it is a binary decision, insignificant or significant, but that is with respect to a threshold. Now, very interestingly, what happens is that this threshold is readjusted at every pass, and readjusted in what manner? To begin with, we start with a higher value of threshold, okay, and then it is a multi-pass algorithm essentially. I mean Shapiro's embedded zero tree wavelet, or what is more commonly, I mean I would rather than calling it as embedded zero tree wavelet, such a long name, I would call it as EZW. Okay. So, it is a very popular term, okay, that you will be finding in the wavelet encoding literature, okay, about the embedded zero tree wavelet or the EZW coding technique. Now, EZW is a multi-pass technique. So, we first have a higher value of threshold, okay, so that we can, I mean decide about the significance and the insignificance, okay, in a harsh way. Okay. Anything which is really having high values would be considered to be significant, and anything which is less than that would be considered to be insignificant. But then what happens is that with successive passes, the value of threshold is halved. So, if say for example, that we have an array, say let us consider some example array, that would be good. Okay. Let us say that we have 3 levels of decomposition. So, I just pick up now 8, 1, 2, 3, 4, 5, 6, 7, 8, okay, and here 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, okay. So, 8 by 8 is an array that I consider, okay. Now, I partition it. So, this is the level 1 of partitioning. So, that every partition is 4 by 4, and then I partition this further. So, that every band is 2 by 2, and this 2 by 2 is also partitioned. So, that we have got 1 by 1, up to 1 by 1 we can go. Now, let me write down some typical example numerical values. Okay. So, this is an encoding example. And we have a value of 127 here. Here we have got a value of 69, here minus 37, here minus 18, 24, 73, minus 18, 8, 44, minus 87, 65, 18, minus 15, 21, 29, minus 56, 13, 5, minus 8, 5, minus 6, 7, 15, 4, 8, minus 11, 14, minus 3, 0, minus 2, 3, 7. Then come to this subband 34, 38, minus 18, 17, minus 27, minus 41, 11, minus 5, 6, 17, 5, minus 19, 32, 26, minus 7, 5, come to the last band, that is the HH, 3, minus 9, minus 2, 1, 0, minus 1, 0, minus 3, 2, 0, minus 3, 1, minus 1, minus 5, 7 and 4. So, this is an 8 by 8 array. I have just put up an example case of 64 different values. Now, if you examine this array, what do you find? You find that the maximum value of the coefficients given in this example is 127, right. 127 is the maximum value. Now, what is being done is that to start with, we normally choose a threshold, okay, which is less than half of the maximum value. Okay. So, if the maximum value in this case is 127, so the initial threshold, let us say T 0, should be 127 by 2, okay, which is 63.5. So, let us say that we choose a threshold equal to, so we actually make the threshold to be slightly greater than this maximum value x max, mod of x max, we have to say mod of x max by 2. So, that we choose in this case T 0 is chosen to be 64. 64 is a good number, it is 2 to the power 6, a binary number, and it will be very easy to make it halved in successive passes. So, we begin with T 0 as 64 and then we examine this array. So, what happens is that this coefficient value 127, okay, this is a significant value, right. Now, significant value, not only is it significant, it has got a sign, the sign is positive. Okay. So, it is not only significant, it is significant with a positive sign. Look at the next value, that is 69. Okay. This 69 value in the HL3 subband, this is also a significant. Okay. Come to minus 37, this is not significant, because in this case the threshold is 64 and the mod of x is 37, which is less than the threshold. So, this is not significant, this is not significant. Again, in this HL2 we will be finding that the 73 is significant. Here in this subband, what you find, minus 87 is significant, 65 is significant. Any other significant you can explore? No. So, now let us say that we come to this coefficient minus 37, this is not significant. Now, is it forming a 0 tree root? Minus 37's descendants are what? Minus 37's descendants are 44, 87, 65, 18. Okay. Out of this, minus 87 is significant, 65 is significant, but this is insignificant. So, we start with an insignificant, that is 0, but its descendants are significant. So, it is not forming a 0 tree. But look at this minus 18. Minus 18 is insignificant, its descendants are these 4 coefficients. Now, again these 4 coefficients, individual descendants are lying here, all of them are insignificant. So, minus 18 is an insignificant, you can call it as a 0, and all its descendants are zeros. So, minus 18 essentially forms a 0 tree root. Okay. Now, what can we call as this minus 37? It is a 0, but it is not a 0 tree root. Okay. And the coefficients which are significant, that could be either a positive significant or a negative coefficient or negative significant, and the coefficients which are insignificant, they could be either an isolated 0, means not having the descendants as zeros, or they could be 0 tree roots. So, for every coefficients we have got 4 possibilities of encoding. It could be positive significant, let us say PS. Then coefficients could have negative significance. So, this could be negative significant in S. This could be 0 tree root ZTR, let us call, and it could be isolated zeros IZ. So, whenever we are encoding the coefficients, every coefficient, we have to remember that we have to encode the coefficient in one of these 4 categories. Okay. But the beauty is that if we find a 0 tree root, if a coefficient is having 0 tree root, then its descendants need not be searched, because 0 tree root automatically means that beyond this everything is 0. Now, a thinking would come to you that how effective would this technique be, because if we do not find such abundance of zeros, okay, then is it going to be a very efficient methodology? Very luckily, yes, you will be finding lot of such insignificant coefficients, and because of this you will be encountering 0 tree roots. You will be finding that mostly the higher frequency subbands, okay, are having more insignificant values, and that is why it should be possible for you to detect more number of insignificant coefficients, leading to more number of 0 tree roots, and more number of 0 tree roots means that it is definitely an efficient encoding scheme, because you are only designating this minus 18 as a 0 tree root. You are not telling that, I mean, you do not have to explicitly tell any further that these values are individually all zeros or these values are individually all zeros, that you do not have to do. So, that is the so there lies some kind of exploitation of the redundancy, okay, and this is what Shapiro's technique has made. So, in fact, I did not complete this example, but you can definitely go through yourself, okay, take an example array like this, and then you can find out that what are the how every coefficient is going to be treated like this. Now, when the first pass is completed, then in the next pass we are going to make the threshold, let us call it as T1, which should be 64 by 2 or rather 32. Next step it will be further halved. So, T2 would be 16. Next step it would be T3 is equal to 8 and so on. Now, why do we make that? To start with, we have put a very high threshold. So, anything which is less than 64 is insignificant, but with higher and higher passes we are bringing down our significant definition. So, we are very strict at the beginning, okay, but we are becoming more and more lenient, okay, as time progresses. What is the essential philosophy of that? Because if you have to generate an embedded bit stream, okay, better start with a strictness, in the sense that only whatever are very significant, I mean at the end of the first pass you will be finding that only a few coefficients you would pick up as significant, and those will be encoded, rest several coefficients would be treated as 0 tree roots, and we do not have to encode that. But if we are having more number of passes, that means to say that if our bit budget permits several pass encodings, in that case we will come to the next level of encoding, and then we will be able to encode more and more coefficients. Okay. If we still have bits left, we can go in for the level T2, we can come in for level T3 and so on. Okay. Now, in this kind of a multi-pass encoding, okay, every pass consists of two things. One is what is called as the dominant pass. Okay. Each pass is subdivided into a dominant pass and a subordinate pass. By dominant pass we mean the coefficients which are yet to be found to be significant. So, coefficients, so dominant pass encodes the coefficients which are yet to be significant. What I mean by this is, let us take this example again. You see, this coefficient minus 37 is insignificant when the threshold is 64, but in the next pass when the threshold is 32, then this minus 37 becomes significant. Okay. So, whichever are lying between a value of 32 and 64, like here this becomes significant, this becomes significant, this 34 becomes significant. There are quite a few values which become significant in the second pass when I make T1 is equal to 32. Okay. So, dominant pass picks up or encodes the coefficients which are or rather coefficients which are yet to be significant, that are identified and they are examined to be isolated zeros or 0 tree roots. Okay. Whereas, the coefficients which are just found to be significant, okay, they have to be encoded as positive significant or negative significant. And then there is a subordinate pass, and what that subordinate pass does is that coefficients which are already found to be significant in the earlier pass, their values or their magnitudes are refined. So, in the subordinate pass, coefficients already found to be significant are refined in magnitude. And how do we do that? It is by a process of successive approximation. What I mean by successive approximation is like this. Okay. Let us say that we have a value equal to 127. Now, initially in the first pass when this value is 64, I mean the threshold value is 64, it is significant. So, we say that this is encoded as a positive 0, positive significant. So, it is having a value equal to 1. Now, 1 means what? We know that it is in the range of 64 to 127, because 64 is a threshold and we know that the maximum magnitude here is 127. So, it is lying somewhere in the range of 64 to 127. This 69 also lies in the range of 64 to 127. All whatever is significant, that lies in the range of 64 to 127, and whichever are insignificant, they lie in the range of 0 to 63. Okay. So, in this case what happens is that we are just subdividing into two such parts. Now, whichever is within 64 to 127, we can encode them as some value in the middle of the range. Let us say we can encode it as 96, and 0 to 63 we can encode it as 32. Okay. Now, next pass we identify that this 64 to 127 range, okay, we just find out that whether it will be in the range of 64 to 96 or whether it is in the range of 96 to 127, okay, or 64 to 95, okay, or it is 96 to 127, and then we approximate the value by a value equal to middle of that range. So, like this there is a successive approximation which is done in its magnitude encoding, and that successive approximation is carried out in the subordinate pass, and the dominant pass basically picks up the coefficients which are yet insignificant. I mean, I should modify the language. Dominant pass picks up the coefficients which are yet insignificant, but become significant in this pass, but become significant in the current pass. So, this is the way whereby the dominant pass will be followed by subordinate pass, and then again we will be we will be reducing the threshold by a factor of 2, okay, and we will be once again carry out a dominant pass and subordinate pass. Again we will keep on repeating this. Now, the basic idea about the successive approximation technique of encoding which is being done in this subordinate pass is that, well, if you have a bit budget, you can more accurately represent the coefficient, and if your bit budget is poor, in that case your value representation is crude. You have to accept that. So, if you can tolerate only a single pass, then a coefficient anywhere lying between 64 to 127 will be encoded as 95 as 96, the middle of the value. And if there is any coefficient which is and if we can go through the second pass, then at least we can more accurately represent whether 64 to 96 or 64 to 95 or 96 to 127. If we go in for another pass, then we can represent it even better. Okay. So, this is something like you have seen that in the bit plane encoding also we have got a very similar philosophy. That means to say that start with the most significant bit plane and then progressively go in for the lower and lower significant bit planes and coming down to the level of the least significant bit plane. So, this way of embedded zero tree wavelet, okay, it is a very efficient technique, and because there is abundance of such zero trees, especially at the beginning of the passes we will be having more presence of zero tree roots. Okay. So, that is why the encoding can be done very efficiently. Okay. Now, although it is a very attractive technique, and in fact one should be indebted to Shapiro, okay, for proposing such a very nice scheme, okay, which I mean all subsequent researchers had accepted this, and this became a very standard technique for wavelet encoding. But there are certain limitations if you try to observe it very closely. One of the limitation is that such a kind of encoding scheme pre-assumes that you are only going in for a dyadic partitioning, meaning that you are only splitting the LL subband, okay, iteratively. Okay. Now, if you happen to split up any subband other than the LL, okay, to have some analysis, okay, then this technique does not work. And another limitation is that it is exploiting the redundancy which is present at a particular position, at a particular spatial position, but across different scales. That redundancy is exploited by having a very efficient scheme in employing this zero tree root concept, but it is not considering or it is not exploiting the redundancy which is present within the the coefficients within the subband or spatially I mean the coefficients which are forming some spatial neighborhood. Okay. So, they are neighborhood similarity of coefficients, that is also not explicitly exploited. Okay. So, when I mean subsequent to Shapiro's paper, as I told you in the reference itself, that Shapiro's paper was published in the year 1995. Okay. And it was subsequently refined further by Syed and Perlman. Okay. So, they had come up with some better scheme, okay, which is called as the set partitioning in hierarchical trees. Set partitioning in hierarchical trees. So, this is called as SPIHT. Okay. And after that, so that was published in I think 96 or 97. I mean unfortunately, I do not have the ready reference with me right now. But subsequent to SPIHT, there was an effort by the research community to develop a standard, an encoding standard, where the discrete wavelet transform can be used. Now, we have been so long discussing about the still image compression standard, and in still image compression standard, as I mentioned, that the first standard that was proposed is the JPEG standard, and still even today JPEG standard is continuing to be used as a very popular technique. Okay. But looking at the futuristic requirements, and especially the requirements for encoding very large size images, okay, which will come with the very high resolution or high definition television signals, okay, HDTV applications, or I mean where the picture resolution will be much higher. Okay. So, there the JPEG techniques would have some limitations, okay, limitations in the sense that one needs a better compression efficiency as compared to the JPEG. So, with that in mind, the standard for the next version of the standard was designed, and that is JPEG 2000. So, as the name implies that JPEG 2000 was addressed, the work for JPEG 2000 began with an objective that it should be completed by the year 2000, okay, to formulate the next generation of standard for still image compression. There was some delay. So, I think that by the end of 2000 or beginning of 2001, the standard was proposed. Now, JPEG 2000 has used the discrete wavelet transform coding. So, this has used DWT coding, whereas as you already know that JPEG had used DCT encoding. Okay. Now, in JPEG 2000, the DWT encoding, how was it used? Now, one approach could be to use the EZW, because I mean the technique which we already described, but because of its limitation a better technique was explored. Okay. But yet the people who framed the standard, they had kept one aspect in mind, okay, getting the inspiration from Shapiro's algorithm, that even the new standard which is going to be designed, okay, there one should have a very or rather one should adopt a an embedded encoding scheme. So, the embedded coding scheme was not dropped. So, embedded approach was still considered, but the encoding, instead of doing it in the Shapiro's zero tree wavelet way, okay, it was done by considering the significance within the subbands. It was also a multipass kind of a subband, but it was done with an objective that rather than dyadic partitioning, any other way of partitioning also can be employed. Okay. And then the redundancy is present within the coefficients, redundancy is present for the coefficients within the subband, that was also exploited. And the technique that was adopted there is embedded bit streams or embedded block coding. Let me write down the words fully. Embedded block coding with optimized truncation of the embedded bit stream. A very long word, a very long sentence it is, okay, but every time we talk in terms of abbreviations, embedded block coding, then the basic philosophy is optimized truncation, and this is called as EBCOT in short form, or EBCOT. Okay. Now, embedded coding we are familiar with, because Shapiro's technique is also a kind of embedded coding. Now, here it is called embedded block coding, because the subband, the samples within the subband or the coefficients within the subband, they are subdivided into blocks, okay, and it is encoded blockwise. So, there is a block coding, and the beauty behind this technique is the optimized truncation. Why optimized truncation? Because even in Shapiro's algorithm, it is said that you can truncate the bit stream, and when you truncate the embedded bit stream, okay, you are going to lose information, but I mean till the point where you have truncated, okay, at least its quality should be preserved. But the truncation point could be anywhere, and at least I mean near about the truncation point you are going to lose some information, and which is going to create some error in the reconstructed image. Whereas, in the case of EBCOT, they adopt an optimization technique, a rate distortion optimization technique, so as to specify some specific points of truncation, some specific points at which the bit stream may be truncated. So, it is a kind of a quality versus bit rate trade off which is specified, okay, because it is going into a standard. And the man behind this EBCOT or embedded block coding with optimized truncation of the bit stream is David Taubman, and there is yet another classic paper by David Taubman which you should read. Okay. The reference of that is, author is David Taubman, Taubman, Taubman. High performance, the title of the paper is High Performance Scalable Image Compression with EBCOT. The paper appeared in IEEE Transactions on Image Processing, volume 9, number 7, July 2000, page 1158 to 1170. So, this is also a very important paper, you should read that. This EBCOT algorithm is actually the one that has gone into JPEG 2000. EBCOT in little bit of modified form. I mean, what Taubman proposed is slightly different from what finally the JPEG 2000 had adopted. Okay. Now, you may find the initial reading of the paper little difficult because of the lot of details and intricacies which are there in the EBCOT, but okay, if you patiently read the paper, you will be developing the interest and you will come to know that how the JPEG 2000 is JPEG 2000 bit stream is encoded. The essential advantage behind this EBCOT algorithm is that this permits one to very efficiently encode the region of interests, okay. And as I was telling you already, the scalability trade off, the quality bit rate scalability can be very nicely achieved using this EBCOT algorithm. So, I am not going into the details of EBCOT algorithm, okay, just to make a mention, and the rest is up to you to study it further, okay, just to give you some direction that where we have in today's technology. So, in the next lecture, okay, we will be going over to the video compression, because so far we have covered all that I wanted to talk on the still image compression. In still image, we have covered the DCT and the DWT as techniques, and as standards there are only two standards, the JPEG and JPEG 2000, but we will describe the basic philosophy behind video coding in the coming lecture. Thank you.